Hey physics students, welcome to Rapid Review for Honors Physics. Today we're going to be talking about Newton's laws. I would like to emphasize today the first and second law, and if I can go rapidly enough for this rapid review, we should be able to get that knocked off in a reasonable amount of time. There's so much to say. Let's take a look at it. First and second law for today. First of all, how did Isaac Newton get credit for saying an object at rest stays at rest? Like, isn't that obvious? My students thought so. When they drew cartoons of Newton's first law, they were like, duh, of course it stays at rest. But less obvious to people, historically especially, was that an object in motion stays in motion. People historically observed that something moving tended to come to a stop. They didn't know what caused it. We now know that's friction and air resistance and stuff like that. But it took a while for people to figure out that an object in motion stays in motion. So best we could do in our world to eliminate friction and air resistance, best I could think of, was a hockey rink. And my students who play hockey have assured me that it's possible to get that puck moving all the way across the ice from one end to the other, so therefore not too much friction. Now, Newton's law says things stay at rest, they keep moving unless acted on by an external net force. Oh, now we have to define that. What's a force? Oh, well, that's a kind of a push or pull, kind of what you think it is. What does net mean? Net means the vector sum. Net is like net profit. You take all the money you made, you subtract out all the money you had to spend, that's your net profit. So here, net force is the same thing. It's a vector sum taking into account the pluses and the minuses appropriately. External also is important. It's kind of what you think it is. I'm emphasizing it now because it's going to be especially important later. You have to keep in mind what object you're studying when you're talking about forces that are external to it. Okay, so in summary, the first law says, I'll read it, an object at rest stays at rest, and an object in motion stays in motion unless acted on by an external net force. Okay, fine, but what if there is an external net force? Then what? Let's find out. So Newton's second law talks about the answer to that question, and it says, if there's an external net force, then there will be some acceleration, okay? There's external net force, there's some acceleration. That's what happens. The rest is detail, but the detail matters. Let's get good at it. The law says that if you have a net force, which is a vector, you'll get some acceleration, which is a vector, same acceleration we've been using all along, and there's a constant of proportionality called mass that we haven't done much with. Mass is effectively, you can think of it conceptually as the resistance to changing motion or the resistance to acceleration. We'll dive into that a little more here. If you're interested in units, I will not read this detail, but I show here, if you want to freeze your video, why it is that 1 Newton is the same in units as 1 kilogram meter per second squared. So Isaac Newton got to have a unit named after him, and that is the Newton. It's 1 kilogram meter per second squared. The second law has some implications. If we have an external force, the object will accelerate. We discussed that already. How much acceleration you get depends on the mass. If you have a big mass, you're going to have a little acceleration. For a given force, if you have a little mass, you're going to have a big acceleration. That's just how the equation works. Always worth it when you're looking at a new equation to think about it in those kinds of terms. What if I doubled this variable? What would happen to this other variable? Good habit when you see a new equation. Let's come down here and mention what mass is. I already told you, it's sort of like the resistance to changing speed, or more specifically, the resistance to accelerating. And also loosely, you can think of it as the amount of stuff. Do not use it as weight. Don't use the word weight, use the word mass. Weight is something else. We'll get into that later. Okay, You will hear the word inertia. I don't use it a lot. It's just a word that people thought of a long time ago, and it's the resistance to changing motion, or the resistance to acceleration. We quantify that with mass. So I'll talk about mass a lot more than just the idea of inertia, which is just a tendency of something to want to keep doing what it's doing. Okay, now often when we solve force-related problems, we draw force diagrams. That little gift box I show here is nothing special. It's just a placeholder so I can put some forces on it. Here I have a 10 Newton force pushing to the right. That is a net force, therefore, of plus 10 newtons. As always, the length indicates the magnitude, and the arrowhead direction indicates the direction, as we discussed when we introduced the idea of using arrows for vectors. The direction matters. Here, I'm showing a minus 10 Newton force because it's pointing to the left. Balanced forces look like this, a plus 10 and a minus 10. Net force is 0. So those are all algebraically added as you would expect them to. Now here is one of the trickiest things. You may have discussed in class, is this object accelerating? Is this object moving? Right? A lot of people will look and say, oh, there's no net force, it's not moving. Not true, right? Because remember, Newton's law talks about acceleration, not about velocity, right? So no net force means no acceleration. It's possible to have something moving at constant speed. There's no acceleration, no net force, okay? So keep that in mind. It's very tricky, and it often causes people to trip up. So if forces are balanced, there's no net force and there's no acceleration. But be careful, if you have no acceleration, that means something might be going at constant speed, which means it could be moving at constant speed or not moving at all, which is a special case of constant speed, which is standing still with a velocity of 0. Okay? We'll use this slide more as we go, but that's a quick preview of a thought process that we'll use a lot. In summary, the first two laws say this: object at rest stays at rest, object in motion stays in motion, unless acted on by an external net force. And can't say it any better than this, second law, F net equals mass times acceleration. Stay tuned for the third law, as you might have expected. That's coming up in our next episode.